Okay, so this week we're going to talk about work, power, and energy. In part one, we're only going to talk about work. So in part two, we will talk about power and energy, especially their relationship to one another. So after this lecture, you should be able to define mechanical work and distinguish between the differences of positive and negative work, as well as defining energy, kinetic energy, gravitational potential energy, strain energy, and then the relationship between work and energy, as well as power. So work is the mathematical product of force applied to a body and the amount of displacement that the body undergoes in the direction of the force. So the direction is going to be extremely crucial, especially when we are talking about mathematical relationships and solving equations or problem sets that we do in class. But the overall conceptual definition of work is the means by which energy is transferred from one object or system to another. So the equation that we're going to use for work is U equals F times D, where U equals the work done, F is the force applied to the object, which is important to note is going to be measured in newtons, and then D is displacement of an object along the line of the action of force measured in meters. So the overall units that will be used for work is the Newton meter, or Nm, which is otherwise known as a joule. So what I will have you put on any quizzes or exams or practice problems is actually notifying or signifying your answer using the joule rather than Nm as your variable within your answer. So to calculate work, we're going to need the force and the displacement, but what's important to note is that we are going to need the average magnitude of force. So if you think about when you're pushing an object across a table or moving an object in some direction, the force that you apply could vary or change throughout that movement, all right? So we don't want the peak force or the least amount of force. We want the average magnitude of that force, or the average amount of newtons that we impart upon some object across that entire movement, okay? Something that we also need to be aware of is the direction of the force. So is it positive or negative? And we also need to know the displacement, or the magnitude in the change of position, which is going to be considered along the line of action of the force. Okay, so this, based on, or what you should have known from last week's lectures, it can be in the vertical or horizontal direction. Okay, so it's either going to be your change in y or your change in x, which is going to represent your overall displacement. So to discuss how, or an example of work being done on an object in an anatomical movement, we're going to talk about the phases of the bench press. So in our example, he is starting 75 centimeters above his chest. He's going to descend the bar down to 5 centimeters above his chest, and then raise the bar back to 75 centimeters. So in this example, we're going to assume that the bar is 1,000 newtons. So the average force that is going to be imparted on the bar is positive 1,000 newtons. All right. Now we're going to talk about first the ascent of the movement, where it's starting 0.05 meters, all right? Because remember in the picture, it was 5 centimeters, all right? So it's 0.05 meters, and the bar is going to end at 0.75 meters, or at 75 centimeters, okay? Now, our displacement in these two examples, the ascent and the descent, is going to depend on whether he is going up or down, as to whether it's positive or negative. So in the ascent, or when he is raising the bar, we know that his average force is going to be 1,000 newtons, and his displacement is going to be equal to 0.75 meters, which is his y final, which is at the top of the movement, minus 0.05 meters, which is his y initial at the bottom of the movement. So based on the variables that we know, u is going to be equal to 1,000 newtons times 0.70 meters, which is going to come out to 700 Newton meters, or 700 joules. However, in the descent, or lowering the bar, he is still using an average force of positive 1,000 newtons, yet his displacement is going to change here. So his y final is going to be the bottom of the movement at 0.05 meters, and his y initial is going to be the top of the movement at 0.75 meters. So his work done for the descent is going to be u equals 1,000 newtons times negative 0.70 meters, which is equal to negative 700 Newton meters, or negative 700 joules. So when you're calculating work done on some type of object, especially in an anatomical movement, it's important to know the difference between a positive and negative work, both mathematically and conceptually. So if you get a positive mechanical work done within some type of mathematical equation or problem solving, you should know that the positive work is done by force acting on an object if the object displaces in the same direction as the force. So if the force is going to the right, the object should also be going in that same direction. So two examples of this is going to be throwing a ball or throwing some type of object. Your force imparted on that ball and the direction in which the ball is displaced should be the same. Same thing in a jump takeoff. Your muscles are imparting a certain force that is going to propel you in some direction. Usually if it's your entire body jumping off the ground, that is going to be your ground reaction force that is aiding you in propulsion. So the force that is placed on you as well as your displacement should be going in the same direction. However, if the object is being displaced in one direction and a force is applied in the opposite direction, then you are going to have negative work. So two examples of this would be catching a ball and a jump landing. If a ball is being thrown and is being displaced to the right, the force of catching the object is actually going to be in the opposite direction. Same with a jump landing. Your body is being displaced downward, but the ground itself is going to impart a force in the opposite direction. Now, if you take these same concepts and apply them in an anatomical example with muscle contraction, positive muscle work is going to come when a muscle contracts and its points of attachment move in the direction of the muscle pull. So if you think about elbow flexion, right? So this is your shoulder and this is your hand, and say you're trying to move a dumbbell upwards, all right? Your bicep is going to be attached up here at your shoulder and then below your elbow, okay? So when your bicep contracts and these muscle attachments are moving up, the object itself will also move in the same direction. So in this particular example, you will have a positive muscle work, okay, and a concentric muscle contraction. So the bicep is contracting in a concentric manner, meaning this angle is going to get smaller. However, negative muscle work is going to come when a muscle contracts and its points of attachment move in the direction opposite that the muscle is pulling, okay? So if we go back to our elbow example and say that you are starting with an object here, again, this is your shoulder and this is your hand, and say you are slowly lowering a dumbbell down, okay? Now your bicep still has to contract in the same direction, because muscles don't contract in opposite directions, they only pull, okay? Muscles only pull, that's important to know. Now, if you're slowly lowering this, say it's a dumbbell, you are allowing gravity to essentially take over and move this object down. So in this scenario, even though your force of the muscle is pulling up, the object is moving down in this direction, all right? So the displacement is opposite of the force. And in this scenario, from a muscular contraction perspective, this is going to be an eccentric contraction. So this angle, this joint angle, is actually getting larger while your bicep is still imparting a force. Now, if you think about our other muscle contraction type, an isometric contraction, does this isometric contraction perform mechanical work? Now, the answer to that from a strict mechanical perspective is no, okay? Now, the reason for that is in an isometric contraction, the displacement, the D, is going to equal 0, right? Because in an isometric contraction, that joint angle should not change. So the displacement should equal 0, which would render U equals FD would equal 0. So from a mechanical perspective, your work would be 0. From a physiological perspective, your muscle is imparting or working in some sense, but within this course and within especially this conceptual framework, the answer to this question would be no. So that is the end of part 1, and we will talk about energy and power in part 2.